even though we have the idea and the the development speed is much small, less than those people in the large big groups and industries. So what I think right now is that collaboration maybe also is another way to research that conflict. Because in our engineering part, we think about algorithms, how algorithms works. But most like biology motivation will be help to borrow from some other collaboration group, research group from other biology departments or other chemistry department to see whether what kind of specific problem for two related approaches or pencil for the will become solutions and let the students involved in specific problems. And I think this also I feel quite works very well.
Yeah, yeah. I wanted to add. Okay. Okay. Yeah. That's an interesting comment. So even for AlphaFold 2, I know it's demonstrating CASP, it's working so well, right? But I don't have evidence, but I believe it's still depending on individual problems, individual kind of proteins. For example, we already observed some of the presentation. It doesn't work that well for small proteins. It doesn't work that well for a certain kind of memory proteins, just because the learning process doesn't have that enough data. Maybe down the road, when there's enough data, they could still do better. But it's a myth that we should not just believe in that. We should really dig up how well it can do in your particular problem. For example, after we really apply to the cryo-EM image data, we notice sometimes it doesn't do that well. So I believe there's still enough room for academia type of work to really make it do better. Maybe using AlphaFold as a tool somehow to help your problems. It should not be something we completely believe in.
And one more thing, the fact that scooping is a phenomenon means that it's a very young discipline or a topic. And so from my experience, exactly what was said, facilitating these sort of interdisciplinary, cross-disciplinary projects with biologists and chemists, I think there's a higher chance that two people or even more with different perspectives will be able to identify a problem that nobody else has identified. And then you're the first to attack it and you're ahead of the curve, and then you're going to scoop somebody else. So definitely there's opportunities there.
Okay. Yeah, thank you for mentioning other fields and interdisciplinarity, because I think also one thing that's very important is improving communication between like something that comes from computer science, like machine learning and AI, with chemistry and biology, with people who have a different kind of background. And how can we improve this communication? Like I'll give just an example. So I've been in a project once that I came as a computer scientist to the problem, and someone saying, well, just do machine learning and you get everything, right? So there is this tendency to believe that it's this magical tool that will just give you answers. But how can we communicate that to the community, to other scientists, about the challenges and the problems that this field is facing right now?
Yeah, kind of related to your question. So many years ago, we also had this workshop, actually 2007. It's the first time we had this workshop. So you've seen the group's presentation of the papers. For a long time, none of these groups actually knew anything about machine learning. But look at now, almost every of these groups are doing machine learning.
because we are forced to learn so. But I think there's still room. The black box needs to be opened up. That's what I think. And there's really a lot of gaps. As a scientist, computer scientist, PhD student, I really hope you guys go in deep there. Open up this black box. Really visualize what's flowing from one layer to the next layer. And you might be surprised how much you can, how much new things you can do. Yeah. So I really don't like this black box concept, and hopefully we can work together to really explain as a scientist.
And then from my experience, what I've seen is computer science students, very technical. 23 layers, convolutional, et cetera, et cetera. That sort of chatter is not, I'll say, it's not well received by somebody in biology and chemistry, for example. So I've experienced that maybe steering conversations towards, a specific task or what is the problem from a biological perspective, and then slowly start introducing these, technical concepts. And I've reached out to chemistry faculty in my institution, and there's no shortage of problems that they need to solve. So I found from experience that listening first to the problems and then saying, oh, well, maybe there's this tool, and then going deep into the technical aspects, I think that often has a much better chance of success than simply starting with, oh, there's this new deep learning thing and it can do everything for you, and you spew out all these technical aspects, and that's often a conversation ender. So I think there's a finesse to how communication is facilitated, that it's both technical and sort of problem-based, specific to a chemist or biologist.
These are good points. Anybody else in the room who wants to add to this? Or on Zoom, or feel free to use the chat if you have any comments. Someone.
Yeah, just like I agree with what you said. I think one way to understand what is really needed in this community. So we all work in the interdisciplinary projects, right? It's really important to also go to chemistry and physics conferences. So I know it's very challenging for us. I mean, I've been going to ACSBW, so I was a junior PhD student, and I remember the first time I maybe understood it was 5 to 10% of what they were explaining. It was very technical, all chemistry, and I just attended a computational chemistry session, but it was still very easy. And I'm still going there as a faculty, and I would say that really I'm not stupid. But I think it's really important for us to be present in different areas, because that's how we can educate ourselves to understand what is the gap, and also communicate that with our collaborators, right? So if they want something, they want a tool, we go and understand what they exactly want, and they encourage them to come to this conference to understand what are the tools here. So I think that's actually the very exciting part of the research, working on these interdisciplinary problems. We can have everyone on board, and that I think when new ideas are presented. So yeah.
Thank you.
I think there was another.
Oh, there's another one.
No, you get on it.
Okay. All right. I think we're kind of approaching 4:40, which is the end of this panel, so it's kind of too short. There's too much to talk about. So I just want to ask our panelists to, either give you what you think structural bioinformatics will look like in a few years, or maybe 6 months from now, or just any overview or anything you want to add to this that we haven't discussed that you think is important we should also talk about.
I'll do just quickly. Yeah. I think it's going to, machine learning, deep learning is still going to be a main topic, because it's a important approach. It's an important method for us to study. So I'll be expecting more of this type of work. But I hope we can see more of the in-depth discovery inside of the framework. If anybody next year bring a paper like that, I will be really happy to see.
And I will add big data. I think, well, deep learning to be accurate in any regard needs a lot of data, but fast forward 5 years from now, and the data that we think is big now will be little. And I've seen in students them grappling with that big data. Just what do you do when you have so much of it? Just ideas and concepts that are not really related to machine learning or deep learning, but are required of the bigger framework. Understanding what big data is and being able to twist it and manipulate it, I think that's an important thing. So I'm not saying that's the future of machine learning, but as data gets bigger, I think we will have to become more and more adroit in being able to manipulate it and store it and, you know, unzip it or whatnot. Yeah, lots of challenges.
Okay, anybody else from the audience would like to ask that? Yeah, one question.
How about from students, right? Any of the students?
Oh, yeah, I know.
Oh, go first.
So, my question for the panelists here is, the mother of engine is necessity, right? And how do you get that fire of necessity in students? Well, students come. Are you gonna, are we gonna have a field too? I know we are. So how do you get that fire of necessity burning?
Ooh.
I guess ultimately is the desire to discover. It's if you like figuring things out, that's the ultimate most force inside, I think. And as a for people who've gone through the PhD process, and I just think that's a natural training process. By the end of the PhD, you will feel like you want something new. And that's the probably eternal force.
Yeah. Which students find very exciting, I think. Something new, something that nobody's ever done before. It sounds scary, and it is, but then it's exciting as well. So I think articulating that to students helps.
Okay, thank you for commenting the questions. I guess we need to wrap up because we have talks coming up soon. So thank you very much. If anybody has any final comments on Zoom, feel free to enter when we say bye. So I want to thank very much our panelists and everybody who joined here and joined on Zoom. And also I want to thank the NSF for funding students to come here and present their papers. It's really great to have that opportunity. And I hope, my hope for next year is that, you know, like machine learning is everywhere now, including structural biology. And as the panelists said, my hope is that we'll crack open the black box and look under the hood and figure out what's actually happening, like get actual biophysical insight about what's going on. I think, I don't know, we all here have something to contribute. So hope to see you guys again next year at CSBW and talking about the new advances in a year from now. So thank you all. Thank you guys on Zoom.